Tonight's webinar is Reflective Optics for Multispectral Systems. My name is Dave Alexander. As John said, I'm a senior manufacturing engineer at Ophir Optics Group. Senior just means that I'm one of the older people still at Ophir. We're an MKS Instruments brand, and let's get right into our agenda. Tonight we'll be discussing the many challenges of reflective optics for multispectral systems. We'll discuss the background, applications, design of manufacturing, and capabilities and actual performances. But first, a few words about Ophir and MKS. And Ophir is an MKS brand. Ophir is an MKS Instruments company. MKS, a world-renowned company, traded on NASDAQ. Last year's revenue was over $2.3 billion. Ophir is part of the Light and Motion division. Optical solution business comprised of the Ophir Optics Group, which designs and manufactures the highest quality lenses for IR imaging system and also for high-power lasers. Also, the optical components business, the OCB, which is a manufacturer of high-performance grating, optical filters, and replicated mirrors. And also the integrated solution business, the ISB, provides solutions for initial design and the volume manufacturing. The OSB Group has a global presence of 7 manufacturing sites with approximately 800 employees overall, which makes it one of the largest optical companies with the widest capabilities for designing and manufacturing optics, from the deep UV to the IR, optical components, and complete assemblies. The Ophir Optics Group has 2 sites. I'm speaking from the Israeli site, and we have a site in Bucharest. We have approximately 360 employees total, and we make over 300 or 400 optical components annually, and approximately 150,000 assemblies yearly. The Ophir Optics Group delivers end-to-end solutions from build to spec, build to print, and the widest commercial off-the-shelf products portfolio available. Ophir products answer the commercial and the defense industries, developed together with these industries and for these industries. We provide solutions for aerial, security and surveillance, maritime, automotive, and the past year actually, for fever detection, which because of the COVID-19, we've had quite a bit of orders in that area. And also in the defense, we supply airborne, land, and naval armies worldwide. Now let's get right into the background of multispectral reflective systems. Multispectral systems, in general, combine several imaging bands from the visible through the IR, and even along IR, allowing significantly improved performance without increasing size and weight. They generally have long focal length, which means we can see further. And generally, these systems have lenses and also mirrors. The mirrors is what we're going to be discussing mostly in this seminar. The reflective mirrors are able to give excellent multispectral reflectance over a very wide spectrum. And also, the mirrors we can attain very low roughness, which is very, very significant when dealing with the UV and their visible spectrum. These mirrors are based basically on the Cassandrian telescope, which is generally a pure parabola, which is a primary mirror, and the secondary mirror, which is attached in a special place in the middle. Now let's look into applications. There are day and night systems built for built for airborne payloads, providing high performance even in harsh weather conditions. These multispectral systems, imaging systems, combine multiple optical channels in one pod, which allows significantly improved performance and reduced size and weight, thanks and because of the large optical mirror, which is actually the heart of the system. These large mirrors provide high-level performance across a wide range of wavelengths. The mirror reflection angle is identical for all the wavelengths. The mirror is the key enabler for the folded optical design that reduces the size. And because we can attain minimum roughness, we can also deal with short wavelengths. Now let's look a little bit more closely into how we design and manufacture these mirrors. One of the main considerations in designing the mirrors is actually the raw material that you want to make the mirror out of. We'll look into a few different options, and also the geometrical figure we must consider also. The back, if you want a tower or just no tower, the height, and also where to even put the datum surface. Now, one of the most recent contributions to these multispectral mirrors is a relatively new type of aluminum, which is a rapidly solidified aluminum, which is made by rapidly cooling millions of degrees in seconds. This makes a very nice aluminum, which is comparable to actually nickel-coated aluminum. Conventional aluminum is generally gives a little bit larger roughness, between 4 and 8 nanometer RMS, while the RSA will give between 1 and 2, similar to nickel coating aluminum. One of the disadvantages of nickel plating, though, is that it will cause a bimetal effect. The bare aluminum, either the standard aluminum, the conventional aluminum, or the RSA aluminum, is a pure metal and won't give a bimetal effect. But once you coat aluminum with nickel, it will cause a bimetal effect, which is when two metals have different coefficients of thermal expansion. When they're heated or cooled, one metal will expand faster than the other, thus bending the body. And this bending is detrimental to a precise precision mirror. Now let's look at the actual geometrical figure consideration. Often, we design mirrors at Ophir. We design with a tower in the middle. What's good about the tower is that the tower can be also dimensioned together with the main mirror with a precise reference surface where we can attach the secondary mirror. So it will be precisely at a good point, and there's no third body in between. One of the disadvantages of tower is that it's known to obscure a lot of the light coming in. So we also design an Ophir with just a central hull with a third chassis outside to hold the secondary mirror. Also, a very important geometrical figure consideration is how to design the back of the mirror. The back of the mirror is actually what holds the mirror onto the diamond turning machine. And a good design for the back will allow us to hold the mirror well, so there won't be any vibration and there won't be any stress induced into the mirror surface. So when you consider the back, it's very important to have a good mirror back. If you look at first, one of the main important considerations have as much surface area as possible on the back. So if you look at the diagram with a big red X, this has there's a small surface area on the back for the size of the mirror that you want to make. And also another terrible design error that we try to avoid is putting in screw threads. Because screw threads, will cause distortion of the mirror surface when you put a screw in it. So if you look at with the diagram with the green check, you'll see the mirror on the bottom, and on the top it's flat, the same diameter as the mirror, and there's absolutely no screw threads there. So you have a nice flat surface which we can mount very nicely onto our machine, which makes it easier for manufacturing and enables very tight positioning tolerances. Now let's go into the actual manufacturing, how we do it at Ophir. There's actually 5 different categories that we worry about. First, we have to control the environment. Then design internally, which is the most time-consuming part of the whole process. And there's the cleaning of the mirrors and the measuring of the mirrors, which also can take quite a long time. And then the coating, which is also quite important. But the coating actually gives a multispectral. Okay. Now the controlled environment. When controlling the environment, we have to control the environment also in the rooms where we manufacture the mirrors, where we measure the mirrors, and also in the rooms nearby. They have to be under pretty good control. Because if you look at a 1 degree change in a 200 millimeter diameter mirror, that'll cause a change in length of approximately 5 microns. This distortion will be seen on the mirror face. So it's very important to control the environment to better than the best you can. So we have our rooms controlled, and we have our diamond turning machines controlled. Also, where we have the measurement, we have those in controlled rooms, which are protected from turbulence also. Now, here at Ophir, we have over a dozen diamond turning machines available. They're the most high-performance single point diamond turning machines available on the market today. They're temperature controlled, and we have actually several new machines available. Also, another important consideration are diamond tools. The diamond tools must be precise, the tip must be precise, it must be robust, and it must be very sturdy to be able to cut such a precision mirror. So after the mirror is done on the diamond turning machine, we have to get it off and we have to clean it. So out here we have special solvents to clean the mirror, and these solvents help clean the mirror because the cleaning process is critical to ensure uncontaminated surface. Also, we have to have special holders, which you can see on the right, a special holder to hold the mirror so they'll be cleaned properly. It must be completely cleaned of any oils or any pieces of any chips or anything. So a clean mirror will enable better coating adhesion and good surface quality, so there won't be any staining. Okay, the next step in the process is measurement. Now, there's several different methods that we use at Ophir to check the surface parameters of our mirrors. The most common method is using computer-generated hologram, or CGH for short. And here on the left, you see a small diagram of how a CGH works using an interferometer, and the CGH is placed in the path of the mirror, and you get a interferogram of the surface, and then you can measure it and see how good it is, or if it's not so good, we'll have to cut it again. Another common practice is using the collimation method, but this only works for a pure parabola. And you also need a large flat mirror with a perforation in the middle. That's what you see in the middle. You see a large mirror, which is, I think, that particular mirror is 300 millimeters in diameter. And then the mirror is analyzed. The top picture on the right is the typical analysis of a large mirror. And underneath you see an analysis of the roughness of a similar mirror. And the last step, if everything goes according to plan, we send it to coating. There are several types of coating, mostly protective silver. These two are examples of our most popular coatings. And these coatings is what actually makes the mirrors multispectral. The coating on the left has more reflection in the visible area, and the coating on the right, you'll see if you look closely, it has better reflection in the IR, in the infrared area, from the short IR until the very long IR. And now we'll discuss some capabilities, performances, and we'll actually see an actual case study right now. Here we see a multispectral electro-optical payload. And this case study proves once and all that large mirrors for multispectral systems is a very cost-effective and the best design-to-cost solution in production quantities. Here you can see a payload with a multispectral telescope mirror, a laser illuminator, electro-optic camera, a laser designator, and a mid-wave IR lens, and a day-night system. This is all in one system. It has several different bands that you can see here. You got several different channels. These combine into an electro-optical system with all channels combined into one system, thanks to the large multispectral mirror, which allows significantly improved performance while reducing size and weight. This actual system is in service today all over. It has a large diameter. It's almost 300 millimeters in diameter. And the wavefront error, as you can see, is very, very impressive, lambda over 40. And in summary of tonight's lecture of multispectral systems, multispectral telescopes, here I listed a few typical capabilities that we have available at Ophir. We basically mostly do bare aluminum. We usually do not do nickel coating, but we do it. Our typical capabilities are up to 300 millimeters in diameter, and our surface accuracy is typically half a fringe, with roughness of approximately 3 nanometers, and scratch and dig is pretty good at 60/40. Now, if you have any other needs, any more demanding or less demanding, we're always available for questions and comments. I want to thank everybody for coming tonight. Especially want to thank the team at Ophir, the team at Laser Focus and Endeavor and Photonics, and all the people that helped with tonight's webinar. This is David Alexander, waiting for questions. Thank you very much.
You're very welcome,
okay.
David, and thank you for the great presentation. Now we'll start the Q&A session of the event. If anyone in the audience has a question for David, please enter it using the purple Q&A icon on the toolbar. Let's see. We've got a question. I'm wondering, it says, can you manufacture off-axis mirrors Do you have freeform capabilities?
Sure. We've done that, been there. How do you say it in English? Been there, done that. We have very good capabilities for freeform and for off-axis. Of course, it depends how big an off-axis. Any more questions, John?
Yeah, thanks, David. The next one asks, what is the biggest mirror diamond turned you can manufacture?
Ooh. Let me see. I've been here with Ophir a long time. The largest one I remember manufacturing was over 400 millimeters. Maybe it was 500 millimeters. But there's two things to consider here. One is the machine, the diamond turning machine, which is capable of taking up. Our largest machine can take even a 700 or 800 millimeter mirror, but then there's the issue of measuring it. Yeah.
Yeah. So are you doing CG8s for general A-spheres?
We use CGHs, and we have designed and manufactured a few, but we do use them, and we generally purchase them from different manufacturers. But we have made our own.
Okay. Next question is freeform more costly or more or less the same compared to, say, aspherics? For example, silver-coated, 1 nanometer rough, 100 millimeter wide mirrors.
That's a difficult question for me to answer. In general, I'm not sure if I understand the question. If he means just the coating, then the coating doesn't really matter what surface is being coated, but the actual diamond turning of a freeform is generally more expensive than a simple A-sphere. So that's a general answer to a general question.
Okay, thanks, David. The next question is, how is high-speed cooling accomplished?
That's something we don't do. This is something that the producer of the special aluminum does, and you can see on their website, I'm not sure if I remember, but what they do, they have a very small stream of high-heated aluminum, and they cool it very quickly.
The next question asks, do you give service and consultation during the design stage?
Oh, yes. That's one of our specialties. We recommend strongly that the designers get in touch with us during preliminary design and concept. We offer the service based on basically on commitment that you'll come to us and manufacture in the end. We have several customers that we have this very good relationship with.
Very good. The next question to ask is freeform? Oh, that's the one we already answered. Let's see.
It's still more.
I think we have one last question. One last question
Yeah.
that asks, which market do you serve?
Oh, we serve military market, also commercial market. We do lots of things. Like I said in the beginning, we've made components for many military systems that I'm sure you heard of. And recently, the past year, we've been making a lot of lenses for commercial applications to check people's temperature before they come into malls or whatever.
Okay, David. Well, that answers all the questions. On behalf of Laser Focus World and today's sponsor, MKS Ophir, I'd like to thank our speaker, David Alexander, for his presentation here at the Photonics Next event.